we're going to work an old problem in a new way in section 4.2.2 using the remainder theorem. If a polynomial f of x is divided by x minus k, then the remainder is f of k. This means you can evaluate a function with synthetic division. A 0 of a polynomial function will result in a remainder of 0 when performing synthetic division. So there's a lot of information here, and we've covered quite a bit, so this following list will help us to understand the notation for all these different aspects. All of the following are equivalent statements. Number 1, x equals k is a 0 of a polynomial p of x. Number 2, x minus k is a factor of p of x. So notice when we studied quadratic equations, we said if this is a factor and I set it equal to 0 and solve for x, I would end up with the solution x equals k. So here we're just making an association between what the factor looks like and what the 0 looks like. Now, if we know that k is a 0 and x minus k is a factor, then we could write that as an ordered pair. K0 is an x-intercept of the graph of p of x. So zeros, factors, and x-intercepts are all related. Number 4, p of k equals 0. And that's basically the definition of 0. If x equals k is a 0, then that means when I plug it into the function, the result is 0. Finally, number 5, the remainder when dividing p of x by x minus k is 0. So notice the function value is the same as the remainder, and that's what the remainder theorem is about. As I mentioned at the beginning of this video, we're looking at a new way to work an old problem. So let's apply this remainder theorem on example 2. Example 2 says, use the remainder theorem to find the requested function value. The function is f of x equals x squared plus 5x minus 4, and we need to find f of negative 2. Now, let's pretend for a minute that we don't know what the remainder theorem is. And that may be true at this point. You may be still a little fuzzy on what exactly it means. But if I asked you to find f of negative 2, I bet you would know exactly what to do. We're going to call this our old school approach. F of negative 2 is obtained simply by plugging negative 2 in for x in the given function. So we would obtain negative 2 squared plus 5 times negative 2 minus 4. When we evaluate, we get 4 minus 10 minus 4, or negative 10. So the function value here is negative 10. Now, let's look at it in light of our new remainder theorem. We'll call this our new school approach. We're going to apply the remainder theorem. So back up here, the remainder theorem says if a polynomial is divided by x minus k, then the remainder is f of k. So what we're going to do is take the argument of our function, in this case it's going to be negative 2, and we're going to use synthetic division with the given polynomial, and we're going to figure out what the remainder is. The remainder is the same as the function value. Here's what it looks like in practice. I'm going to take the argument of the function as is. Notice I'm not changing the sign, just putting the argument into the box. I'm going to pick up the coefficients of the original polynomial, 1x squared plus 5x minus 4, and we will run our synthetic division process. Now, make an association between this spot, which is the remainder, and the answer we got on our old school approach. Notice those are exactly the same thing. So we're looking at a new way of working an old problem. To find f of negative 2, previously we just plugged negative 2 into the function and calculated the output. Now we're taking the argument of the function in our synthetic division process, and we're recognizing this last spot, the remainder, is the same thing as the function value. So we can say, therefore, f of negative 2 equals negative 10. Now, if that spot happens to be 0, then we know our function value is 0. And if our function value is 0, whatever lives in that box is a 0. So let's work example B. G of x equals x cubed plus 2x squared minus 15x minus 16. And we're looking for g of 1. Let's use the remainder theorem. So I'm going to put the argument of the function in the box, and I'm going to pick up the coefficients. Notice we don't have any missing terms. And we can run our synthetic division process. The remainder spot here is the function value. So we can say g of 1 equals negative 28. In my opinion, calculating a function value like this is easier than plugging the number into the original function, doing it the old school way. With synthetic division, you're either multiplying two numbers or adding two numbers at once, whereas the old school way, you plug it in and you have to add up and multiply a bunch of things all at once. So I think this is a really simple process. Now, let's make some further observations about this problem. We have worked the problem. Negative 28 is the answer. The problem is complete. So this is just for your understanding. We could say ordered pair x equals 1, y equals negative 28 is on the graph of g of x. We can see the input x value and the output y value. We can also say that x equals 1 is not a 0 of g of x. It is not a 0 because the function value is not 0. Therefore, we know x minus 1 is not a factor of g of x. So if I were to attempt to factor that polynomial, at least I can rule out x minus 1 as one of the factors. Another thing that I want you to pay attention to on this approach to the problem, notice whatever's in the argument position, I put in the box and do not change the sign. The only time I change the sign is if it is given in the form of a factor. In that case, I would change the sign of this number to put it in the box. So watch out for that subtle difference when you're working your homework. If you want to pause the video for a minute and evaluate k of negative 1 using the remainder theorem, then unpause and we can work it together and see if you got the right answer. So in the box, we will put the argument negative 1. Now watch your coefficients here. Notice we have x to the 4th. X cubed is missing, so we're going to need a 0x cubed. We've got x squared. X is missing, so we're going to need a 0x and then our constant term. So the appropriate row of constants would be 1, 0, 2, 0, and negative 8. Running our synthetic division process, bring down the first number. Negative 1 times 1 is negative 1. Add vertically to get negative 1. Negative 1 times negative 1 is positive 1. 2 plus 1 is 3. Negative 1 times 3 is negative 3. Add to get negative 3. And negative 1 times negative 3 is positive 3. So we end up with negative 5. Therefore, k of negative 1 is equal to negative 5. The function value is the same thing as the remainder. And that is our remainder theorem.